In this lecture, we're going to study a concept called demand paging. So what is demand paging? Note that in modern complex systems, the main memory is not always enough to store all the pages of all the active processes, right? Because every process might have a large address space, it might have a large number of pages, and not all of them may fit into the limited main memory of a system. In such cases, the operating system uses part of a secondary storage device like the disk. So part of the disk is earmarked as swap space in order to back up some of the pages of processes that do not fit in memory, that are not actively being used. Note that if a page is being used, if the CPU is issuing load and store instructions, then that page has to be in memory. But a page that is not currently being run on the CPU, a page that the CPU is not currently executing, those pages can be stored away into the disk as part of the swap space, right? So for example, you can see here is process 0. It has 3 pages, right? There is page 0, which the CPU's some instruction on this or data on this the CPU is currently accessing, therefore it is in main memory. And this process also has page 1 and page 2, which it hasn't used in a while, therefore these can be stored in disk. And when the CPU requests for them, they will come back into main memory, right? So this is what is called the concept of demand paging. Physical memory is allocated on demand, only when needed, only when that page is actively being used, right? So here we'd like to introduce a new term called as a page fault. So if you recollect, we've seen that there's something called the present bit in the page table entry. This indicates if the page is currently residing in main memory or if it is swapped out to the disk, right? So when translating from the physical address, from virtual address to physical address, the MMU first reads the present bit. And if the page is present in memory, okay, well and good. The MMU will go ahead, return the physical address, the CPU will access the location. But if the page is not currently in memory, then the MMU cannot go and read the disk, right? So then what will the MMU do? It will raise a trap to the operating system saying the CPU wants to access this particular page, but it is not in memory, so please do something. And this trap is what is called a page fault. In some sense, it is nobody's fault that this is happening. So the word page fault is not the right term, but this is what has been historically used. So what is a page fault? A page fault is the trap that occurs when the CPU accesses a page that is currently not residing in memory. In such cases, the MMU cannot return any physical address because there is no physical location for that page in memory. In such cases, the MMU raises a trap. And what does the operating system do to handle this trap? This, as like any other trap, this page fault also moves the process from user mode to kernel mode. Whichever process is running, it stops. The CPU shifts to kernel mode. The control comes to OS code to handle the page fault. So the first thing the OS will do is it will find out where this page is stored in the swap disk. It will find out the disk address of the page and it will tell the disk to read that page, right? So the operating system, whenever it swaps a page out, it will keep track in the page table saying this page I've stored it at so and so location in disk, so it knows where to fetch from the disk. And while the disk is fetching this page, disk takes a very long time to fetch as compared to the CPU. So the CPU cannot stay idle waiting for the page to come from disk, right? So the OS switches from this process that page faulted to another process. The current process is moved to the blocked state and the operating system, it's already in kernel mode, right? Handling the page fault. It moves to another process. It performs, it invokes the scheduler and performs a context switch. Then what about this poor process that page faulted? Eventually, when the disk read completes, the disk will raise an interrupt. It will tell the operating system, hey, I'm done. Here's your page. Then the operating system updates the page table of the process. It says, okay, so and so page, I've got it from the disk. I've placed it in this frame number. It will update the page table with the proper frame number, set the present bit, and then it will mark the process as ready. Earlier the process was blocked, now the process becomes ready to run when the disk is completed its reading process. And at a later time, when the operating system decides to context switch again, this process that was marked as ready will get scheduled again, and the operating system restarts the process. So now, earlier there was a page fault at certain instruction, right? The operating system restarts that instruction. Now hopefully there won't be a page fault again. Why? Because the page has been fetched into main memory, right? So this is what happens during a page fault handling. So finally, this is the final summary of what happens on a memory access, putting together all the concepts we've learned, like the TLB and page faults and all of that. So when the CPU issues a load instruction for a certain virtual address, right? This could either be some code, the CPU could be fetching an instruction, it could be loading some memory location into a register, whatever it is, the CPU issues a request for a certain virtual address. So the first thing that happens is the CPU cache is checked, right? Not all CPU memory requests go to the memory. The CPU has its own cache, which is outside the purview of operating systems. You would have learned about it in an architecture course. There's level 1, level 2, level 3, multiple levels of caches for modern CPUs. So the cache is checked first. Is that address, is that byte present in cache? If yes, the request is satisfied from the cache. If not, the CPU decides to come to main memory in the case of a cache miss. Now, while going to main memory, what happens? The MMU intercepts that request and it has to translate from the virtual address to physical address, because the main memory does not understand virtual addresses. So now it comes to the MMU, right? So you've gone from the CPU to the cache, and if the cache is a miss, then you've gone to the MMU. And this MMU will eventually help you access memory. Okay. So what does the MMU do? The first thing the MMU does is it looks up the TLB. If it is a TLB hit, all well and good. For this virtual address, you know what the physical address is. You go to memory, fetch that location, give it back to the CPU, and the CPU can continue execution. If it is a TLB miss, then we are in some trouble. Right? The MMU must first go to the memory, probably make multiple memory accesses to walk through the outer page tables all the way to the inner page table, find the page table entry corresponding to this virtual page number, and it will fetch the page table entry after walking the page table. Right? Now, one of three things can happen. If the page is present in memory, it's a valid page, it's present in memory, well and good. The MMU will get the frame number, physical frame number, translate from virtual address to physical address, access the memory, returns the data to the CPU, right? That is the first case, if the page is present in memory. If the page is not present in memory, but it is a valid access, the virtual address is valid, but the page has been swapped out to disk, to the swap space, it is not present in memory, then what happens? The MMU raises a page fault. Because it is not in memory, it cannot return anything back to the CPU. It raises a page fault. Then the operating system handles the page fault. We've seen that before, right? The process is blocked. The operating system comes in. It issues a read to the disk. When the disk read completes, then the operating system schedules the process again and restarts the CPU load instruction. At that time, hopefully, again, you go back, right? You restart the load instruction and you go back here. You do all of these steps again, but at that time you're not going to have a page fault again because the page is in memory. The page will be fetched and given back. The data will be given to the CPU. And finally, the last case, once the MMU has accessed the page table entry, it could also happen that it is an invalid page access. That is, the address doesn't map to anything meaningful. In such cases, the MMU traps to the OS, and the OS once again gets into the picture to handle this trap, and probably if the process did something stupid, it will terminate the process or take some such action. Right? So on every memory access, every time the CPU issues a load or store instruction for a certain virtual address, all of these steps happen. So there could be more complications in a page fault, right? When the operating system is servicing a page fault, it has to bring a certain page from disk to main memory. What if there is no free space in the main memory? What if all frames in the main memory are being used? What should the operating system do in such cases? It must take an existing page, write it to the swap space, free up that slot in memory, and then bring a new page in there, right? It has to swap out an existing page to the disk and then swap in the requested page, right? So there's a lot of work involved. So to avoid doing this on every page fault, the operating system might in the background, when the disk is free or when it is free, it might decide to proactively swap out some pages to keep a list of free pages handy, right? Some operating systems can do this. So now the interesting question comes, which page do I swap out? I have a list of pages in my main memory. All of them are, pages assigned to some process, and now some other page from the disk has to be got into main memory. For that, I have to identify one of these pages, write them back to the disk to get a new page into main memory. So the question is, which page to swap out to create a free slot? So that is what is decided by the page replacement policy of the operating system. Given a list of pages in main memory, which one should I kick out to make space for a new page? That is what is called a page replacement policy. So there are many page replacement policies. Modern operating systems use complex page replacement policies, but let's just study a few simple ones. Right? So what is the most optimal page replacement policy? Which page would you want to kick out to the disk? Ideally, you'd want to kick out a page that is not going to be needed for the longest time in the future. But of course, this is not practical, right? How do you know what pages are going to be accessed in the future? We cannot predict the future. Therefore, the optimal policy is just something that, we can sort of theoretically calculate, but it's not something that can be practically implemented. A very simple policy that you can easily implement is the FIFO policy, first in, first out. You remember when each page was brought into memory, and when your memory is filled, kick out the page that was brought into memory the earliest, right? The first page that was gotten goes out. But of course, this may not be a very good policy, because the page that you're throwing out may in fact be a very popular page, and you might again immediately want to access that, and you might page fault again for it. So the page that you're pushing out to the disk should ideally be a page that you won't use very often, so that you won't incur many page faults. So a common policy that is used in most modern operating systems is something called least recently used or least frequently used, right? Some variant of this is used in operating systems. What does this policy say? Replace the page that was least recently used in the past with the hope that something that was not used very much in the past will not be used very much in the future. Therefore, it is okay to push it out. Right, so now we are going to just run through a simple example to understand these policies. Let's start with the simple optimum policy, the optimal policy. Consider a simple process that has 4 pages, pages 0, 1, 2, 3, and you only have 3 frames in physical memory. Right, so not all 4 pages can be accommodated in physical memory. Sometimes you might have to push one of the pages out to the disk in order to get a new page in, right? And these are the set of accesses, right? This is also what is called the reference string, the list of page references that are generated. Suppose the process accesses page 0 followed by page 1, 2, 0, 1, 3 and so on, right? So in such cases, let's see with each policy what is the number of page faults that you get. So when you access page 0, do you get a page fault? Yes. So the first few accesses always we are assuming result in a page fault, right? Because initially there's nothing in memory. As you access page 0, 1, 2, these are what are called cold misses. These page faults will always happen because there's nothing in memory initially. That's our assumption. So the first 3 accesses will always result in page faults, and now you've gotten pages 0, 1, 2 into memory. Now you access page 0 again. What happens? It is already in memory, all well and good. You access page 1, it's well and good. Now the interesting part is what happens when you access page 3. Right? Look at this row. Page 3 is not in memory. You only have pages 0, 1, 2 in memory. So now what happens? You must evict something out. Which one will you evict? Your optimal policy says look into the future. Which is the page that is not used farthest out into the future? It is page 2. Therefore, the optimum policy will evict page 2. It will remove page 2, replace it with page 3. So now your memory has 0, 1, 3. Then the next few accesses go fine. 0, 3, 1 go fine. Once again, when you access page 3, what happens? Page 2, what happens? It's not in memory. You evict page 3, you bring page 2. And so you have 2 page faults with the optimal policy. Right? This is of course a very toy example. So what happens with FIFO, first in, first out? Usually this does worse than the optimal policy, and there's something called Beledi's anomaly that says sometimes as you give more pages, the performance of FIFO might get worse, right? Because the pattern, the first page that you're evicting, might somehow be a popular page, right? So let's run through the previous example for FIFO. What happens? The first few pages, there's a page fault for 0, 1, 2, and after accessing these pages, your list has 0, 1, 2 in memory. So now the first page fault happens here when you access page 3. Which page will you evict? We've seen the optimal policy evicted page 2, but FIFO will evict page 0. Why? Because that was the one that came into memory first, right? So FIFO evicts page 0. But what happens? Immediately again there's a page fault. Why? Because immediately the next page, unfortunately the next page used is 0. So again there's a page fault. Now what happens? You evict 1. Then again a few accesses later, you're once again accessing page 1. There's again a page fault. Now what is the oldest page among the pages you have? It is page 2. Therefore you evict page 2. And so on. You can work through this example and you'll see that FIFO in general has slightly worse performance than optimal. It's not the most sensible policy out there. The policy that makes the most sense and is roughly equivalent to optimal in this simple example is the LRU policy. So here is your list of least recently used pages. By the time you come here to this page fault, if you look at the past accesses 1, 0, 2, right? 1 and 0 were more recently accessed and 2 was least recently used. Therefore, you decide to evict page 2. Right? So the LRU maintains a list. Any page that is accessed is towards this end of the list. Any page that is old is towards this end of the list. Therefore, you go ahead, evict page 2. And if you work out through these examples, you're going to see that LRU also has only 2 page faults. Right? So therefore, it is in some sense, in the simple example, it's equivalent to optimal. That's not always the case, but for the most part, for most workloads, LRU works relatively well. Why? Because there's something called locality of reference. A program accesses certain pages and then moves on to some other part of the memory image, accesses some other code, moves on. Because of that, if a page has not been used recently in the past, it's unlikely that it's going to be used again in the future. So how is LRU implemented? Because most operating systems use some variant of LRU, let's spend some time understanding how do you implement LRU. The operating system has a list of pages, but the operating system is not involved in every memory access. The CPU issues load store instructions. They go directly to the MMU. The MMU fetches the page from RAM, gives it to the CPU. So the OS doesn't know every time a page is accessed. So how will it know once there's a page fault? Suddenly, how will it come to know which page was least recently used? So this requires a lot of work by the operating system to get this information. And usually you need some kind of help from the hardware. So this is where the accessed bit of the page table entry comes in. Whenever the MMU accesses a certain page table entry, whenever it accesses a certain page for its translation, it will set the accessed bit, saying, okay, I access this page, I access this page. Otherwise, the operating system has no way of knowing which pages were accessed, which pages were not, right? Therefore, the MMU sets this bit. And periodically, the operating system looks at this access bits of all pages to estimate, okay, in the past so much duration, a lot of these pages were accessed and these pages were not accessed. Therefore, it can classify pages into some hot and cold pages or active and inactive pages, and when a page fault occurs, when it needs pages, it can try to kick out pages that haven't been accessed recently. And also the OS, most operating systems also look at the dirty bit. If a page is modified recently, then using that page would require writing to disk again. So the operating system tries to pick pages that have not been accessed and have not been modified, right? So most operating systems use some variant of LRU that is practical enough to be implemented.